Welcome to a comprehensive overview of signals in Unix and Linux. In this video, we'll explore the fascinating world of signals, a crucial mechanism for communication and control within these operating systems. Let's dive in and uncover the details together. Signals play a pivotal role in the architecture of Unix-like operating systems such as Linux. They provide a means for the kernel, other processes, or even a process itself to send succinct one-way messages that indicate urgent events or requested actions. Since signals are asynchronous, the target process can receive them at virtually any time during its normal execution. Over the next few minutes, we will delve into what signals are, the various ways they're employed, and the practical steps you can take to handle them safely. By the end, you should have both a conceptual grasp and a real-world sense of how signals enhance communication and control among processes in the Linux environment. A signal can be described as a minimal, distinct message that notifies a process or even a group of processes of a significant condition or event. Upon receiving a signal, the process learns only the type of that signal, which is typically represented by a numeric code alongside a symbolic name. This constraint highlights the asynchronous and lightweight nature of signals. They're not designed to transport extensive data. Instead, they essentially communicate something happened, react accordingly. Originally introduced in early versions of Unix, signals let the operating system and user-level processes interact without requiring shared memory or more comprehensive inter-process communication methods. For instance, when the user presses Ctrl+C, the terminal driver sends the SIGINT signal to the foreground process, requesting an interruption. Although signals began as a way for the OS to report hardware or software anomalies, like an invalid memory reference, they have proven useful in many other scenarios. Developers now utilize them to coordinate processes, stop or continue program execution, send requests to daemons, and trigger custom routines for more flexible system management. A signal is, essentially a short, asynchronous message. Examples include SIGINT, SIGTERM, and SIGKILL. These messages carry no large data payload, making them lightweight and efficient. While signals can, serve as a simple form of inter-process communication, their primary role is to control processes in response to critical or time-sensitive conditions. The POSIX standard, along with Linux, defines a variety of signals. Let's take a look at some of the most common ones. SIGINT, or signal number 2, is generated when the user presses Ctrl+C. It typically causes the targeted process to terminate unless the process has been programmed to handle it differently. SIGTERM, signal number 15, is the default kind signal sent by the kill command. It advises a process to shut down gracefully. SIGKILL, which is signal number 9, is a non-negotiable termination signal. The kernel immediately stops the process and it cannot catch or ignore this signal. SIGUP, or signal number 1, was historically tied to terminal hang-up events. These days, daemons often interpret it as a prompt to reload their configuration files without fully restarting. SIGUSA1 and SIGUSA2 are signals reserved for user-defined actions. Since the kernel doesn't use them internally, developers are free to assign any functionality or notification they need. SIGKILL, signal number 17, notifies a parent process that one of its child processes has either completed or stopped execution. Without handling SIGHLD or waiting for child processes, you might end up with zombies lingering in the process table. SIGABART, which is signal number 6, is dispatched by a call to abort to indicate abnormal program termination. SIGAFPA, or signal number 8, points to a floating point or arithmetic error, like, say, dividing by 0. SIGSEGUR, signal number 11, occurs when a process tries to access memory outside its valid address space, what we call a segmentation fault. To see all the available signals on a modern Linux system, you can use the command kill L. This prints both signal names and their numbers, though, the specific numeric values can differ across operating systems or architectures. Each signal in Unix has a default action that the kernel applies when delivering it to a process. Common defaults include terminate, where the process ends immediately upon receiving the signal; ignore, meaning the signal is effectively discarded, and execution continues as if nothing happened; core dump, where the process terminates and the system writes its memory state to a file for post-mortem debugging; stop, which halts the process's execution until it receives a continuation signal like sigcont; and continue, which resumes a process if it was stopped. So if a process hasn't made any changes to the default handling, the kernel's response is consistent but, potentially abrupt. For example, sigint typically kills a program unless the developer has set up a custom handler to catch it. One significant advantage of the Unix approach to process signaling is that you can override most default actions. By installing a signal handler, you tell the operating system to call a particular function or even a script snippet whenever the specified signal arrives. This flexibility allows your program or script to perform any safe final tasks before it terminates, or, to ignore certain requests entirely if that makes sense for your application. In C or C++, the SIGAction system call is the robust method for intercepting signals and specifying what routine to run. It replaces an older function, signal, which can be, less portable or reliable in subtle ways. Meanwhile, in the Bash shell, a built-in command called trap performs a similar function for scripts. For example, using the syntax trap echo interrupt caught cleaning up. Sigint would instruct the script to print a message and do any needed cleanup when the user presses Ctrl+C instead of immediately exiting. In addition to altering how signals are handled, Unix and Linux allow a process to block certain signals temporarily. A process that has a signal in its signal mask does not process that signal immediately. Rather, the signal becomes pending until the process removes it from the mask. Once unmasked, if the signal is still pending, it is then delivered. This mechanism ensures that code inside a critical section is not abruptly interrupted by a signal at an inopportune time. For instance, if a program is about to update shared memory or a global variable, it might block specific signals that could disrupt that update. After completing the sensitive operation, the program can unblock those signals, allowing them to be handled in a controlled manner. System calls like sigproc mask sigpending and sigaction help developers manage which signals are blocked and how they should be handled once unblocked. If you think of signals as asynchronous events, then signal masking is akin to temporarily disabling certain interrupts while the system is in a delicate state. Because signals arrive asynchronously, a handler might fire at any unpredictable instant. This unpredictability, combined with the fact that many library functions rely on global resources or internal states, makes writing robust signal handlers challenging. A function is considered async signal safe if it can be called reliably from a signal handler without introducing race conditions or deadlocks. Functions like printf generally are not guaranteed to be safe in this context because they may use non-re-entrant operations. Instead of performing complex tasks in a signal handler, the best practice is to set a global flag, often declared as volatile sig atomic T, to indicate which signal arrived. Return from the handler swiftly, enabling the main program loop or another part of the code to detect that flag and respond safely. This pattern preserves system stability and reduces the risk that your signal handler will disrupt the normal flow of your program in unpredictable ways. When you have more elaborate demands, like large memory operations or I/O within signal context, an alternative, safer concurrency method is typically recommended, such as threads or separate processes using fuller featured IPC. To consolidate your knowledge of signals, it helps to experiment with them in a real or virtual Linux environment. Simple interactions with shell commands and scripts can build the intuition and muscle memory needed for more advanced programming tasks. Bash provides the trap built-in, which is, honestly, an ideal starting place. Suppose you have a script that does some continuous work, like reading and writing files, or maybe checking user input. By adding lines such as trap echo interrupt signal caught, exiting gracefully. SIGINT trap echo termination requested, cleaning up. SIGTERM. You can ensure your script logs a brief message or performs cleanup steps before exiting, or, well, even chooses not to exit at all. If you've previously written a signal_example.sh comma, try extending it to handle a couple of different signals simultaneously. Then, observe how your script's behavior changes depending on whether you send SIGINT by pressing Ctrl+C or SIGTERM using the kill command. Here's an example, trap echo shutting down. SIGTERM, a quick demonstration text in a bash script. Once you've written it, go ahead and run it, then send SIGTERM from another terminal to see how it works in action. Let's talk about the kill command. Despite its name, kill can send any signal, not just those that terminate a process. If you don't specify a signal, SIGTERM, which is signal 15, is the default. For instance, kill SIGINT 1234. This mimics the user pressing Ctrl+C in the process with PID 1234. It's actually quite useful when you want to specifically test your program's response to an interrupt. Kill and kill all. Whereas kill targets a specific PID, kill and kill all allow you to send signals to multiple processes identified by their names or other attributes. For example, kill fpython searches the command lines of running processes for Python, sending a default SIGTERM to all matches. Similarly, kill all SIGUP HETTD instructs all instances of the HTTPD daemon to reload their configuration, leveraging the common practice of using SIGUP for that purpose. Use these commands carefully. Specifying insufficiently narrow criteria might end tasks you did not mean to close. And on a multi-user system, unintended usage of kill or kill all can disrupt the work of other users or even essential services. Signals are one of the earliest and most fundamental communication primitives in Unix Linux. Their asynchronous nature ensures that processes, system utilities, and the OS can promptly coordinate or respond to urgent events. When a process receives a signal, it either follows a kernel-defined default action, often immediate termination, or invokes a custom signal handler if one has been set. Although signals carry minimal data, they can indicate scenarios as varied as user interruption, memory errors, or custom domain-specific notifications via SIGUSA1 and SIGUSA2. Asynchrony. The process may be in the middle of critical code when the signal arrives, necessitating care in handler design. Minimal data payload. Each signal is merely a numeric code, so signals are ill-suited for complex data transfers. Reentrancy requirements. Only certain operations are safe to perform from within a signal handler. Any concurrency unsafe or non-reentrant function call can cause problems if triggered simultaneously with code in the main program flow. For more advanced communication, processes frequently turn to pipes, sockets, shared memory, or message queues. However, signals remain invaluable for simpler tasks, such as shutting down a process, reloading configurations, or dealing with abnormal conditions like segmentation faults. So let's pause for a moment to consider this. Think of signals as event triggers, while advanced IPC acts more like data channels. It's a simple, yet powerful distinction, don't you think? All right, here's an interesting exercise for you. Extend your script, perhaps revise your or a similar bash script, add multiple trap lines to handle signals like SIGINT, SIGTERM, and SIGUP. Then observe closely how each signal changes the behavior of your script. It's quite fascinating to see it in action, really. Now, let's experiment a bit with the command. Start by launching a test application or script in the background. Once it's running, retrieve its PID using OR. After that, try sending it different signals using commands like or even. Be sure to document how each signal impacts the application. It's a great way to deepen your understanding. Moving on, let's explore the AND commands. If you have multiple instances of a command running, this is a perfect opportunity to practice using or to send signals to them. Then use tools like or to confirm their behavior and see which processes remain active. It's a handy skill to have, isn't it? And for those of you who are into C programming, here's a little extra challenge. Dive into the manual pages for AND. These functions will help you understand how to create more robust and concurrency-safe signal handling in your compiled applications. It's a bit advanced, but absolutely worth exploring. By engaging with these tasks, you will gain direct experience with the mechanics of signals, a crucial stepping stone toward more advanced Linux system programming. Understanding signals thoroughly places you in an excellent position to manage process lifecycles effectively, debug abrupt errors, and implement custom control flows for your scripts or daemons. Knowing how to send, catch, and handle signals fosters a deeper appreciation of the Unix philosophy. Keep it simple, modular, and flexible. Processes remain largely independent, but signals offer them a concise way to synchronize, terminate, or adapt to unusual conditions without heavy overhead. While signals do not serve as a general-purpose data conduit, their presence in virtually every Unix-like system ensures consistent behavior across countless environments. As you advance in your understanding, try to incorporate signal handling best practices in any long-running services or scripts you develop. For instance, a daemon that gracefully reloads its configuration on SIGCUP or cleans up after itself on SIGTERM exemplifies the elegance and power of the Unix signal model. Signals, asynchronous, minimalist notifications. Keep exploring to master advanced concurrency and system programming.